the room. I'll let you share your screen.
Oh, yes.
I don't know how to put the cameras of the room, so you will have to just see me. But there are 50 people in front of me.
Okay. Can you see my screen?
Yes.
Yes. Okay. Just
you
give
can
me a
start.
moment.
Almost there. He froze.
Yeah. There's some issue. Just give me a moment. Yeah. So Raja, can you please confirm if my slide is visible?
Yes.
The only thing is that it may not be the full screen mode, but I don't know, there's some issue, as I mentioned earlier.
It's okay. We're seeing your slide.
It's okay?
Yes.
Okay. I believe good afternoon, everyone in the audience, although I don't see you. I hope you all are enjoying this wonderful Quantum Energy Initiative Workshop 2026. Unfortunately, I cannot be there in person. Before I start, I would like to thank the organizer, Raja in particular, for inviting me and giving me the opportunity to speak on one of our recent works. And this work is on fundamental limitations on reliabilities of power and work in quantum batteries. Since there is a time constraint, I will sweep through very quickly. And if there is some question, obviously I will come back to that in the question and answer session. So here's the outline. First, I will say a few words to motivate that why we started this work. Then I talk about reliabilities. What do we mean by reliabilities for quantum batteries? Then reliabilities for particularly in power and work, and also their bounds and trade-off. And then I will use these bounds and trade-offs to study many quantum batteries, which will possibly lead us to talk about some optimal design of quantum batteries. And then I will conclude. So here goes the motivation. I don't think for this particular audience, I don't need to tell you what is the importance of quantum batteries today, because it kind of promises us of novel energy sources, particularly in thermodynamics sense, the work source, which should be enabling efficient energy transfer for quantum technological devices, starting from quantum computation to all other quantum information tasks. And however, if you look in this particular field, most studies are concerned about quantum batteries that are essentially to enhance or having high power and capacity. One thing practically is overlooked for years is that although you may have high power and capacity, but how useful are these, let's say, parameter or let's say quantity of interest? Particularly if there are some fluctuation. Let's say I have a car which is delivering some power, but this power is not steady. In a sense, like sometimes you get high kick, sometimes you get low kick, and so on and so forth. So on an average, you may have high power, but the fluctuation in power, at the same manner, the fluctuation in work output, obviously, of some parameter of interest in order to really qualify a quantum battery, a good quantum battery. So in this work, essentially, we studied that part. And here the reliability is quantified in terms of something called noise to signal ratio, which I will discuss or introduce soon. And in general, we say that if this noise to signal ratio is high, that implies we have low reliability. I think this is kind of from an experimental point of view, we all agree. So here it goes. We kind of, at this particular, at least for this particular work, we restrict ourselves to unitary charging and discharging process. So it's like you have a quantum battery which is closed, and maybe because of their internal quantum cells and their interaction, it may get charged, or it may so happen that you shine with a laser light or some external field with which you can charge it. So as you can see on the screen, So our battery essentially has two components in its Hamiltonian. One is the battery Hamiltonian, another is the charge one, the charging part of the Hamiltonian. So this charging one goes to essentially zero or null operator before and after the charging process or discharging process actually took place. And now I will go on to define certain quantities in particular, just to say that, see, if I consider any observable, for that matter, maybe a work observable and so, this I can always write down for this particular Hamiltonian in the Heisenberg picture, and some effective operator I can always define, that is the time evolved operator minus the operator that is at time equal to 0. Now obviously you understand that the moment I take expectation value of this object in the Heisenberg picture, it essentially will give me, let's consider that this is the battery Hamiltonian, then it will essentially give me the ergotropy. So in that way, essentially, we come up with this, this effective operator, and then use this operator and kind of did some full counting statistic mechanism, and from there, we can find out the average and fluctuation of this object. And let me be very clear here, this operator can be an arbitrary operator at this moment. But whatever that, we can always use full counting statistics to get average value and the fluctuation we have in that particular observable. So with this, you can always define something called noise to signal ratio, which is kind of opposite to reliability in that sense. For let's say observable O0, we can always define the fluctuation in it divided by the mean square, essentially. So you understand that if the fluctuation is very low compared to the mean value, that means your NSR that we call this noise to signal ratio is low. In that sense, it is more reliable. And with this, now we can come up with like the quantity of interest, for example, the work. And for that, we can consider the operator, this O0, to be nothing but your the battery Hamiltonian in this particular case. And obviously, using that, you can always calculate the average, the fluctuation, and the noise to signal ratio. The same also you can do for power, but in that particular case, the operator you have to choose is this object. As you can see, this is the commutation. If you look at very carefully, what is that if you consider H0 as your battery Hamiltonian, then this charging Hamiltonian is nothing but in this commutation essentially indicates how fast this charging Hamiltonian actually evolve in time. So in that way, you can kind of intuitionally at least justify that this must have something to do with the power. And it turned out to be that if you go in that way, using full counting statistics, you exactly find out the average power and also the fluctuation in power and NSR, that is the noise to signal ratio in power. In general, as you can understand that, this work operator and the power operator, they don't commute with each other. So this already says that there is some kind of incompatibility as far as these two observable, I don't want to say observable, let's say the quantity of interest are concerned. And obviously that should in principle lead to something called trade-off, particularly when I shall be talking about this noise to signal ratio of the fluctuations. So with this now let me proceed. So the first thing that we found in this particular paper is that there is a fundamental lower bound for any operator or observable you can consider. Well, I will not go into details. All the details can be found in the paper I just referred. And so this ITO0, which is nothing but the classical Fisher information. So what it exactly means, your state is evolving, but you project it on to the projected space of this operator O0, and then you look how fast your observable on that, or let's say the state on that projected space is evolving. So this is essentially the classical Fisher information, and this F is nothing but the time correlation function, which has little bit non-trivial expression. But nevertheless, what the main point here is that NSR, that is the noise to signal ratio for any quantity corresponding to O, cannot be reduced to arbitrarily low value. And the lower bound can only be attained for particular cases, particularly for choices of some state and Hamiltonian, essentially. Well, this is just to kind of build up the story. But now the question is that if someone wants to lower the NSRs for both power and work for the time being, let's say, to incompatible quantity of interest, let's say, what would happen? And it turned out to be that you cannot simultaneously push them to their lower bound, essentially. And you can kind of understand, as I have indicated earlier, that if you look at the NSR for work and NSR for power, they essentially follow uncertainty-like trade-off relation. This, you can kind of say, it's kind of a little modification of Schrodinger-Robertson equation, where the left-hand side is the multiplication of the NSRs in work and power, and the right-hand side are some kind of commutation and anti-commutation, where the operators or the quantities, the operators, the one I have defined here. It's not the operator, it's the quantity essentially at the end of the day. Well, so this kind of gives you kind of the fundamental trade-off relation. And now we'd like to kind of study the implication of these observations, let's say. And for that, we consider many-body quantum batteries. Although in the paper, we have considered some more cases, but for this talk, and because of the time constraint, I'm just jumping on the main result and main findings. So the moment we apply this observation or these findings so far we have on many-body quantum batteries, we would like to see what happened. So we again consider a simplest scenario where I have spin chain, where individual battery cells, quantum cells, the Hamiltonian of them are represented by the one which is on the left, and there may be some k-body charging Hamiltonian. So k-body means like k number of spin are interacting with each other and so on and so forth. And this HT is nothing but the total Hamiltonian. This is the battery Hamiltonian, and obviously difference of them is nothing but your charging Hamiltonian. And to study the reliability, and in particular, the connection with entanglement, we considered two different sets of model. One is the paradigmatic spin model, another is transverse Ising-like spin chain. So let us start with the paradigmatic model. So this paradigmatic model, if you look at, once again, we have the battery Hamiltonian. So it's like, again, a chain of spins. The battery Hamiltonians, the individual quanta cells are here, which is the non-interacting part. And then you kind of switch on this k-body charging Hamiltonian. And if you look at that, this is exactly like this. Obviously, for fair comparison of different k values, that means as you increase this number of interactions, spin interactions, for fair comparison, we also ensure that the overall norm of the Hamiltonian, particularly the charging part of the Hamiltonian, should be constant. So it's an operator norm. So in that way, your omega k also is essentially adjusted. So now you can understand from here, or may not, just to give you an intuition that this quantity, this k by n, k is the number of spins. So you can understand that these are like the k number of spins, they're interacting with each other, then another k number of spin, then another k number of spin, and so on and so forth. But in total, we have n number of spins. So the moment your k by n, that means when the n is very large, but this k, which is kind of quantifying the number of or specifying the number of spins interacting with each other, is very small compared to the total number of spin. That means this k by n tends to 0. We essentially get a non-interacting kind of charging protocol. But the moment you have k by n that tends to 1, that means you are essentially having fully interacting, fully non-local charging protocol. So just to give you an idea that we kind of scan from k by n tending to 0 to tending to 1. However, in any intermediate situation, if you start with an initial state where all the quanta cells are starting from 0, the ground state, that means the overall ground state is this one, this 0 tensor n, the time evolved state will be an entangled state, which you can probably follow that this should in principle take this kind of structure. So it is nothing but the tensor product of GHZ like state, where the weight of on 0, 0, 0 and 1, 1, 1 are corresponding to this cos omega t or sine omega t, omega kt. Nevertheless, now with this we can again calculate the average power, the fluctuation in power at NSR, as you can see on the left, and the same also you can do also for the average work, fluctuation in work, and NSR in work. And as you can understand from here, is that it just looking at the power part, at least because this is more clear, that as you increase your K, obviously there is this trigonometric function inside, but otherwise, as you can see, that as your K increases, ideally, your power essentially linearly scales. On the other hand, if you look at the fluctuation, this fluctuation, if you look, apart from this trigonometric function, obviously one has to really take into account all the impact on all the effect as you increase or decrease K, but just to give you an impression that although your average increases with K, but at the same time your fluctuation increases even in faster rate, essentially. So what it essentially gives you an idea that, well, your entanglement may help in increased power, but at the same time, it will cost you in increasing fluctuation. And on the other hand, if you look at the NSR, this NSR also has it's proportional to K. So that means as your K, that means number of interacting spins are there, more number of spins are interacting in your charging protocol. That means your noise to signal ratio actually increases. And actually the similar feature also can be visible for work. Although the work, as you can see, just it is K independent, and it makes sense because it's an additive quantity and it just adds up for all individual one, right? And that's why it's just multiplied by N. However, the fluctuation and NSR, they're all dependent on K, and in particular when K increases, they also increase. Well, so one thing from here is very clear. Now, if you multiply, for example, this NSR of this one and NSR of this one, and I would like you to note that this NSR actually getting an equal value, and this equal value is essentially the lower bound that we discussed earlier. This is like the fundamental lower bound for this particular state and the Hamiltonian to start with. Nevertheless, the moment you multiply them, if you look the trade-off relation now, it actually gets you to an equality. And as you can see, this value is K square by N square. So this is a very important point just to note. First, if your K by N tends to 0, that means what? That means you are more towards parallel charging. Then your fundamental trade-off relation approaches 0. So that means apparently it looks like you can simultaneously make them 0 in some way. Not simultaneously, but at least you can say that they both can be pushed towards a very small value, particularly when your charging protocol goes more towards the parallel protocol. On the other hand, if you, because you understand that the moment your K is fixed and N increases, that exactly means that it actually goes to 0 asymptotically. On the other hand, if your K is fixed and you increase on the other hand, if you have your K by N tends to 1, that means all the spin is interacting with all the other spin, and in that way you are going towards fully collective charging, then you see that this N dependence somehow goes away, and at the end of the day you don't gain that much. So that means your fluctuation at the same time, the NSRs still remain non-zero. So what is the message from here is that if you go towards non-local charging, obviously it can boost your power, but you have to pay with the reliability. On the other hand, if you go towards local charging, obviously you may have to give up your power. You may not be able to boost your power that much, but you can improve in reliability. So it's kind of give you a trade-off in between. So we have, as I have mentioned, that we did some numerical analysis on that just to see. And I don't want to go into that much of details as there is no time. But here you can understand this K is the number of spins that are interacting in that sense. And here we have plotted with all these parameters that if you can read, is that for K equal to 2, that means the two spins are interacting, K equal to 3, K equal to 4, and so on and so forth. So this plot essentially tells you how the average work and average power is essentially evolving. So this is the solid line, this is the dashed line, and these are the color code. As you can see, as you increase the K means the number of interacting spins in your charging protocol. So both, at least up to this, both your power and average work essentially increases. However, if you look at the fluctuations, you can also see that as you increase your that K means this number of spins interacting, your fluctuation in work and fluctuation in power also increases, at least to the time which we will be restricting ourselves until we charge completely, because otherwise it will again discharge where we will stop. But as expected, if you look at the NSRs corresponding to work and power, as you can see, they behave in this way. Obviously, if you multiply them, they will give you a standard, it's a straight line corresponding to K by N. So this just to give you an idea that obviously in the paradigmatic model, that is what we should expect. Now we went towards a little bit more realistic model that we call the Ising-like. Yes.
In the next minute.
Yes. So anyway, the same feature also we have seen for Ising-like model and so on and so forth. So what is the end node, if I say in that way, that as you increase power or try to increase power, the fluctuation in power actually increases. While on the work part, what we see that when you have low power, the work fluctuation is more, but in high power, the work fluctuation is less. So in that way, if you can visualize, so here comes the conclusion. We establish a fundamental bound on reliability of quantum batteries through NSRs of work and power. And as you can understand, because of incompatibility, there is some intrinsic trade-off of power and work observable operators. And so that kind of says that improving reliability of power reduces the reliability in work and vice versa. And another point is that collective charging obviously can enhance power or boost power, but it also amplifies NSR, that means noise to signal ratio, reducing reliability. So that means it kind of suggests us that any practical high performance quantum battery should have a trade-off between these two ends, and obviously it should go towards something called hybrid scheme. It's not fully non-local charging protocol. At the same time, it's not fully local charging protocol, somewhere in between, just to balance the reliability performance. And we also understood that entanglement in general may assist in boosting power, but it does not guarantee in increasing or let's say enhancing reliability. So this is essentially the conclusion in this short talk. And before I end, I would like to make some declaration and also an appeal. So the authors of this particular paper, in that paper, we kind of declared something here, what I mentioned. We aligned with the manifesto of quantum scientists for disarmament. Here you can see the archive link. Those who don't know about this, please look at it. And we also oppose any use of our result for military and surveillance purposes. For those who don't know, you can also look at this quantum disarmament manifesto webpage. Look at it, and I really appeal you that you also endorse this manifesto. In addition, we are now living in a situation where in the international arena, there are probably 70 to 80 regional and international level conflicts are going on. Thousands, millions of people are affected, many are dying every day. So to raise and stand against this militarism and destructive use of science and technology, join International Union of Scientists, which just recently came up. Here is the website, and with this declaration and appeal, I thank you. Thank you very much.
Okay,
Raja, can you hear me?
Yeah, can you hear me? I don't know if you
yes.
can hear me. Yes, okay. So we're running a bit over time, so thank you for that mentioning the manifestos, and we will definitely look at that. Does anyone have a really urgent question? If not, I suggest sending questions by email, if that's okay. But if there's a really urgent question, no. So there are some questions, you might get some questions by email, but now I think we will move on to the next talk. Thank you very much. It was a very nice talk. Thank you.
Thank you very much. Thank you very much. Thank you. Thank you.